filmmaker. But you know that when you make fun of the people, I mean, sometimes I'm just thinking that, okay, so, people should know the fundamental principle. Not talking about the society, but fundamental physical principle. And how the universe works, actually. Not the university work, the universe works. It's insane. And they asked me, okay, so if I sit on a plate, what's the consequence? They told me that the consequence is that your membership got suspended. No, I'm talking about physical consequence. Oh, there's no physical consequence, but the universe is just give some random. It's so stupid. Indeed, it's so stupid. I want to emphasize. I hope that the president can see my video. Professor is complaining here. Anyway, so just relax, okay? So this is 3 to 4 minutes to start the class. Oh, by the way, the midterm. For the midterm, we're going to stop. I mean, what I'm going to talk about, okay? So is that what we'll cover in the midterm, okay? I mean, before midterm, we will cover that the behavior of solution, and behavior of solution also be included in the midterm. But after that, after this class or next one, so we're going to talk about the phase diagram that will not be included in the midterm, okay? So that means the midterm covers all chapters before, not before, diagram. Okay? And this one, not included. Okay? Any questions, comments? I think I missed a E here. Anyway. So we're going to start, okay? And for this time, we already discussed all the key information about the behavior of gas. So we talked about the mixture of the ideal gas, and we mentioned about the chemical potential, the partial pressure, that means the Dalton partial pressure law. Basically, that means for the ideal gas, the partial pressure is proportional to the fraction of the molar fraction, okay? So and then we move on to the non-ideal gas. Basically, we consider interaction and the volume of the gas molecule. So because of that, we amend the model, basically the ideal gas equation, and we change that to the van der Waals equation. Okay, based on that equation, we can predict the behavior of the non-ideal gas. Basically, how can we liquefy it, and how the free energy, the Gibbs free energy changes, and what is a critical point, what's the critical temperature, critical pressure, critical volume. We introduce all these concepts, okay? And we also introduce the concept what is the metastable, what is stable, and which is the unstable state, okay? So we also draw the first diagram. That's pretty much the key information. But on the textbook, you also can find there's some other model besides, other than the van der Waals model, talking about the behavior of the non-ideal gas, okay? But if you're interested, you can just go to this chapter by yourself. But that one is not covered in the midterm, okay? But I still suggest you to see that. Okay? Anyway, so today we're going to move on to the next chapter about talking about the behavior of solution. Okay? Before we move on to the next chapter, if you have any kind of like suggestions, comments, or complaint about my teaching, please come to let me know, okay? So sometimes if I cannot express my idea properly, just ask, okay? You don't want to postpone or delay, okay? You are welcome to come to my office if I have any complaint, okay? I'm not the gym stuff. Okay. I will not say that I'm the law, just follow. No. Okay, I'm just the, if you have any questions, okay? So remember one thing, if you don't understand, I mean, this kind of misunderstanding probably going to show up in your midterm, okay? At that time, it's a little bit too late. The reason is that that's already showing your score, okay? But for the other thing is that for the homework, if you have any questions, come to talk with me, we can explain. And you'll have the chance to fix the issue. Okay? If you don't like your score, come talk with me. After you fix it, we can make up the score, okay? It's not one time, okay? But midterm and final one time, we cannot fix later, okay? We can still explain to you, but I will not change the score. But for homework, yes, we can, okay? As long as we make sure that you understand, okay? I mean, give you the evaluation, give you the score is not the purpose of class. The class is to make sure that you understand what we're talking about, okay? Make sense? I'm so reasonable. Anyway, so before talking about that one, we want to, oh, by the way, so as you suggest that follow this chapter very carefully, because when I prepare for the class, I read the textbook. It's awfully rich. Unfortunately, I don't understand what I'm talking about. I think you will have the same issue when you try to read textbook. So that's the reason, try to follow what I'm saying here, okay? I rearrange the discussion at chapter in the textbook, okay? So I hope that I can give you a better explanation about this chapter, okay? So before talking about the first topic we're going to talk about is the ideal solution, okay? So what is the ideal solution? Oh, by the way, so solution here not only means liquid, okay? Solid state, like alloy, we also call it solution, okay? Solution is not about phase, it's about form. Okay, as long as you mix something together uniformly, it's a solution. Okay, you have solvent, you have it's not necessary to be the water and alcohol. That's solution for sure. But the alloy, the zinc and the copper alloy, we also call them the solution. But it's just a solid state solution. Okay, that's one thing we need to make sure. The other thing is we're talking about the ideal solution, but since we're already talking about the liquid or the liquid or solid, in other words, we call them the condensed matter. Okay, you know what's condensed matter? That means in the liquid or solid form. It's not in the form of gas. It's not in the form of the plasma. Okay, is the solution. Then there's interaction. Okay, if there is no intermolecular interaction, it will be in the gas phase. Okay, so when we talk about solution, there should be interaction. Okay, so that's really be very careful when we talk about ideal solution. That is different from the definition of ideal for gas. For the ideal gas, there's no intermolecular interaction, but for ideal solution, there is. Okay? But what we call is the ideal solution. The ideal solution means if we have two types of the particles or two types of molecules, A and B, okay? We know that in between A and A, we have an AA bond, right? That we have an AA bond. And for the pure B metal or liquid, we have a BB bond, right, in interaction. The ideal solution means after we mix it, we also have the AB interaction, right? Ideal solution means the AB interaction equals to the AA interaction equals to BB interaction. Okay? Basically, we do not feel, I mean, if we put the atom A inside the B, the A atom will not feel any difference in terms of interaction. Okay, in terms of interaction. Understand what I'm saying?
So the way AA and BB and AB interact is also going to be the same?
All the same, all the same. The interaction strength the same, the shape are the same, okay? Basically they are the same. I mean, this one indeed happens. Okay, some solution is very ideal-like. That means the interaction is pretty same. For example, like iron and nickel. You mix them together, form the ion-nickel alloy. Basically, the behavior is very similar to the pure iron or pure nickel. Okay? And the zinc and copper are the same. But if you mix the copper with iron, they are not very similar to each other. Okay, I will explain to you what's the difference. Okay. But this is the definition of the ideal solution. Okay. It's not like there's no interaction. There is interaction, but the interaction doesn't change. Okay, that's the ideal solution. So what's the consequence? So what's the significance of it? So think about it. So we have, for example, a piece of A metal, a piece of B metal, and then we melt them to form an AB alloy. Okay, AB alloy. Okay, the interaction between them change, right? Then we have the total internal energy of the A piece is UA, the B piece is UB, right? And the interaction here is UAB, right? So what do we have? Since that the interaction doesn't change, right? Then we will have this conclusion. Correct? So that means the internal energy doesn't change before and after mixing. Correct? Is that understandable? But you know that typically we don't use but this conclusion only holds when the volume doesn't change, right? When the volume doesn't change. But we mix the metal, typically we do not care about whether the volume changes. But we know that the pressure doesn't change. We always perform this one under atmospheric pressure, right? So instead of using the internal energy, another important conclusion is that the enthalpy also the same. Okay? Okay? Also the same. Is that understood? Right? You got the pressure doesn't change. Okay? So basically, can be another definition of the ideal solution. Basically, that means the internal energy or enthalpy doesn't change. Okay, enthalpy doesn't change. Does it make sense? Okay. Then the question is, what's the driving force or the driving factor that can allow us to mix the metal? Allow us to mix metal. Do you have any kind of suggestions? Since the energy doesn't change, the entropy doesn't change, what are the changes before and after mixing? The volume, yeah, it may or may not. Something else changes? Entropy. Okay, the entropy changes, right? This is definitely massier than this two, right? Correct, everybody? So how it changed? Again, we can do some calculation, okay? So the same thing, consider we have A, we have B, and N, okay? So previously, before the mixing, we have totally Na atoms or molecules inside the A piece. And we have totally number of B particles in NB piece, okay? And then after mixing, we have totally Na plus NB. Correct? Is that right, everybody? Okay, so then we're going to see that how many configurations change, okay? So if we assume this one, the entropy of this one, let's assume this one is the well-ordered crystal. Every molecule or atoms just have the perfect order inside it, okay? Then what's the entropy? We can assume the entropy here is 0, right? Because everything is all, I only talk about the configuration entropy, okay? And for the B atom, the same thing. I just use the solid dot to represent the atoms or molecules inside the B. So this is also 0, right? But what about here? It can be something like this, right? You just mix them. Something like this, right? So we need, in order to calculate the entropy, we just need to calculate how many different kind of microscopic.
It's gonna be a lot, right? It's gonna be a huge number of microstates.
Huh?
Sorry.
What was it?
I thought it was gonna be too many to kind of count. We're gonna have to lose the. Don't worry about it. Sorry.
Okay.
I misinterpreted something.
So then, how many macrostate configurations? I mean, macrostate or configuration in this kind of
A lot.
Yeah.
a lot, right?
A lot.
But how many positions?
Makes sense.
How many positions? How many possible positions in this kind of the position? Right now, first of all, let's remove all the atoms. Let's see how many sites, possible sites inside this crystal.
Na plus NB.
Na plus NB sites, right? Then we start to put the molecule inside. So what's the total different type of configurations? Correct? Right? We just do different kind of like the arrangement, right? Huh?
Divide by the same, if something is similar.
Yeah, that's what I'm going to say, right? This is the total number of microstates, right? And then, but we should know that we cannot distinguish two A atoms. They're exactly the same. Two B type, they're also the same, right? Then we need to remove the different order between A and B. Correct, everybody? So that's the number of the microstates. in this kind of very gigantic model, right? So basically, the ask here is NA plus NB is that right? And we know that originally it's just 0, right? It's original. Oh, sorry about. Yeah, you're right. Right? K times ln. This is the definition of the entropy, right?
That is enthalpy, right?
Hmm?
That is enthalpy, right? H.
A is what?
H.
H.
Okay.
Which one is
No,
K?
the previous one. That is enthalpy,
Yeah.
right? Okay, thank you.
You know why the S here is 0, right? Because the microstate is just like N, B, I forgot what's the name of this kind of mark. How was it?
Factorial.
Factorial, yeah. Divided by NB, this one equals 1, right? If we follow the same calculation, this is 1. Then the log 1 is 0. That's the reason the configuration of entropy is 0, right? Okay, so basically, then the change of the entropy is just like K. K is the Boltzmann constant, right? Ln NA plus NB remember that we need to calculate that, right? So do you remember we mentioned something we call is the Stirling approximation? Check your notes. So we mentioned this one before. So basically it means the ln n, when n is very large, ln n factorial, whatever, very large is approximately equals to n times ln n minus n. Okay, so we're going to use that kind of approximation to do this calculation. Okay, then this one equals to k ln NA plus NB ln NA plus NB minus NA. Okay. Minus plus this one, and this term just cancel each other. Right? And what we have here is okay. We add an active sign here. And this one eventually equals to minus k times n ln xa plus ln xb. Oh, hold on, no. Right. It's right. for here, the XA equals to NA, right, NA plus NB, XP equals to NB, NA plus NB. Okay, basically XA and XB are molar fraction of the A molecule and B molecule inside the solution. Okay,
How,
make sense? Huh?
second last line, how do you derive? Second last line.
This one.
Yeah, how it comes.
Oh, see that we just separate this one A ln NA and B and combine with this term, and NB ln NA and B combine with this term. Okay, and we also add negative sign here. That's the reason the positive one become the denominator. Okay, so
Oh no.
sorry.
Just
So one suggestion, Professor, if you write on the right side, you can plot the left side first. Mostly, like if you use that pattern, it will be easy for us to.
The reason I want to keep that part.
Okay. Okay, I can't do anything.
Yeah, it's fine.
this is
Take some, finish the job. Done? Okay. So you can see that they actually change, right? And we know that this one is smaller than 1. This one is smaller than 1, right? Then this term is negative. This term is negative. And we have a negative sign here. Then the total entropy change is positive, right? The total entropy change is positive. So do you think this process can spontaneously happen?
yeah.
Right? Yes, 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 because you want to maximize, right? Okay, so that means although the enthalpy doesn't change, the Gibbs free energy changes, right? This one equals to what? The entropy doesn't change, right? We know that this delta H, if this one equals to 0, right? Correct, everybody? But this one becomes smaller, right? Then the total Gibbs free energy also changes, also decrease after the mixing, correct? Okay, then we can draw something like this, okay? Look at it. This is the G, okay? GM, okay? GM is the molar, I mean this one is the molar. Free energy, okay? And the G, molar free energy, okay? That means we mix it, the entropy going down. Okay, on this part, this axis basically is a fraction of B. Okay, on this end, on this extreme, this is a pure A. On this extreme is pure B. Okay, and in the middle, the molar Gibbs free energy increase. Okay? You know what I'm saying?
Yeah.
So you can see from this one we can also explain why the alloy forms. Okay? Think about at this point, the molar Gibbs free energy of pure A, this one basically is the chemical potential of A. Correct? The molar Gibbs free energy is basically the chemical potential, right? And this point is the chemical potential of B. Correct, everybody? If we just put two pieces of metal side by side without melt them, then you know that at this, for example, at this specific point, at this ratio, when the XB have this specific number, then the total Gibbs free energy should be here, right? Because the GM simply equals to XA mu A non plus XB mu B non. Correct, everybody? if we just put them side by side, right? But if we mix them, then the actual free energy turn out to be at this point. Correct, everybody? So this is the total free energy. Basically, this one is the delta G m, and equals to T delta S, what we already mentioned here. Okay, this is the change. From here to here, okay? From here to here. Okay? And you can see after mixing, the Gibbs free energy drop down. That's the reason this state is the most stable than this state. Make sense? But the question is, after mixing, we know that the Gibbs free energy decreased. That means the chemical potential of A and B also change. Okay? The chemical potential of A inside the mixture is not equal to A none anymore. Okay? The same case for the B. So what's the chemical potential after the mixing? Okay? So, like this. So we know that the GM after mixing is something like this. Okay, this is the before mixing and after mixing. Okay. We know that the mu A none and mu A B, but we want to know after mixing what's that. Okay, we know that the total molar Gibbs free energy is somewhere here, here, or here. But we want to know what is the chemical potential of each component. Okay. So the thing is like this. So look at it. So we do the derivative. I mean, first of all, we make some change, okay? For that one, this one equals to what? This one equals 1 minus xb mu a plus xb mu b. Right? Because remember, xa means the fraction of a, xb means a fraction of b, right? If you plug them together, you definitely get 1, right? So that you, this two parameters are non-independent, okay? xb equals 1 minus xb. Okay. Xa equals 1 minus xb. Okay. This one equals what? This one equals to mu b minus mu a xb. Okay. Make sense? Oh, I see somebody. I see my student. My student. You got what I'm saying? Don't worry, you can come to my office and complain. Okay. Then the dgm dxb equals to mu a equals to mu b minus mu a. Okay. Okay. So we have this relationship. Okay. It's very simple. Okay. You can see what that means. This means basically the mu g is a linear equation of mu x, right? And the slope is mu b minus mu a, right? Mu g minus mu a. And then you can say that if xb equals 0, that means on this end we have a mu a, right? That means the cross, it's the cross section, not cross section. Intersection here is mu a. Okay, that curve, and this one is mu b. And the slope is just mu a, mu b minus mu a, you have something. Wrong side. Okay, you have a linear line here. So for example, we have, let's draw another point. It's not a good point, sorry about that. So let's choose another ratio. Let's choose a ratio here. Okay, let's assume that we have somewhere we feel interesting is here. So this is xb, okay? And of course, from this point to this point, is the t delta s, okay? And we are talking about this point, and then we just do a tangent line. We just do a tangent line on this point, okay? And the intersection with this axis is mu a, and with this one is mu b. Correct? You can see that because the length of this AB axis is 1, right? It's just 1. Then the slope of this curve is mu b minus mu 1, right? Follow this one, and you can see that the cross section intersection on the A axis is mu a, on the B axis is mu b. So it's all follow this equation, correct? So that means if we know the xb, or we know the fracture of B atoms inside the Loy, and we know this the G chart, And then we just need to do a tangent line across this chart. Okay, do a tangent line across this chart. And the cross section on the A and the B indicate the chemical potential of A and B in the mixture. Okay, in the mixture. And you can see the mu A is different from mu A non, and the mu B different from mu B non. Okay, that means their chemical potential also drop. Okay, their chemical potential also drop. So what's the reason for that? Let me tell you what's the reason for that. Okay. Why it changes?
So Professor, we have to know for one, right, to get other, right?
Yeah. What?
Like, how does like you, there is XB, right?
Yeah.
So we take the differentiation of XB and there was no term of XB, that's it, so it mu A already gone, right?
Mu A already
Yeah,
gone.
it
Yeah,
was
yeah.
zero, right?
Yeah, if we put it 0, we put it 0, then the mu B gone. We put it 1, the mu A gone, right? This
Yes.
is 1, this is B, right?
Oh, okay.
Okay.
So we made the mu A is constant, right? That means,
The mu A is constant, yes.
okay.
Yeah, that is a chemical potential in this specific configuration.
So we
So-
already knew mu A.
No, we don't know mu A, we don't know mu B. We only know that XB.
Okay.
We only know XB, okay? For example, if the mixture have different ratio, AB ratio, for example, the mixture is here. So for example, this one XB equals to, for example, 60%.
Uh-huh.
Okay, at this point, probably 40% of the B. Then the chemical potential is like this. Okay, then your mu A is here and the mu B is here. Okay?
So it depends on the curve and the.
It depends on the
Okay.
it depends on the
It
fraction.
depends on that curve and this fraction, right?
The curve is already calculated, right? So
Yeah,
we
yeah,
know that
okay,
the delta
okay.
G is
Yeah,
equals to K NA plus NB, and then is the
Yeah.
XA ln XA and plus XB ln XB, right? So this
Yeah.
one is calculated from this one. Okay? It's calculated from this expression. Okay. So be very careful. Remember this conclusion, okay? Using tangent line, we can calculate the chemical potential because in the next semester when we talk about phase transition, we use this conclusion all the time. This is a way for us to generate the phase diagram. Okay, this is not phase diagram, okay? This is just like the diagram of G. The G gives free energy, but it's not phase diagram. But by using that, we can generate the phase diagram, okay? So I'm going to, probably next semester, I'm going to talk about how to draw the phase diagram by using this kind of a G covenant chart. But in the next semester, in my class, we're going to talk more, okay?
So this is how they draw a phase diagram, not by experimentation.
It's by calculation.
So all the phase diagrams are based on the calculation.
Right now, we are doing calculation because we are talking about the ideal solution. Okay? There's no perfect ideal solution in the experiment. Okay? But we are using this simple model to explain the principle. Okay? But after talking about the ideal solution, we're going to move on to the actual solution. Okay? Any other questions? Okay, we will keep moving. Okay? May I read this part right now? Okay. All right, so we know that this one changes, right? This one changes. So this one is the delta mu A. That's the chemical potential change of A before and after the mixing. And this is the chemical potential change before and after mixing of B. Okay? Why the chemical potential changes? For the solid or liquid solution, I will introduce another concept later. But let's think about it. Let's forget about this is this is the solid or liquid. Let's just think about the ideal gas, okay? Think about the ideal gas. We already know that mu is a function of the partial pressure in T. Correct? The partial pressure in T. Right? The partial pressure drop down, the chemical potential drop down. Right? Right? When you separate them, for example, we have 1 atmosphere of the nitrogen here, and we have 1 atmosphere the pressure of an atmosphere of the oxygen here, okay? And we mix them. So the partial pressure, both of them partial pressure drop, right? Both of them have a partial pressure drop if we mix them, right? The same thing here. So the partial pressure drop, the chemical potential drop. The same thing here. So before and after mix, the ratio of them drop down, then the chemical potential drop down, okay? It's not a very precise explanation, but I just tell you a very rough picture, okay? Basically, that's all for the ideal solution, okay? The most important thing is that remember this tangent law. All right, so after talking about the ideal solution, we move on to the non-ideal solutions, okay? So the key information you want to remember for the conclusion we derived from ideal solution is, after mixing, the entropy change, okay? And the entropy, because the interaction doesn't change, then the contribution to the entropy change is only the configuration or the change of the microscopic distribution, right? Because of that, we call this one is the configuration entropy. And for the mixing of the ideal solution, the only driven factor for the formation of solution is the change of the configuration entropy. Okay, that's it. Energy is the same, enthalpy is the same, only configuration entropy changes. Okay, basically, you have the red bean, you have red bean, you have green bean mixing together. Okay, you cannot separate them anymore. If you want to separate, you have to sit down and pick up one by one. You need to devote some energy, okay, to lower the entropy. But of course, if you want to have two beans, one red bean and one green bean, they are spontaneous separate. Okay, but since the number is so small, it's not a statistic problem anymore. Okay, we move on to the non-ideal gas. A non-ideal solution, okay? So still remember what's the definition of an ideal solution? The interaction doesn't change from A to B, right? AA interaction the same to AA, AB interaction same to the BB interaction. Okay, but what is the definition of non-ideal solution? The interaction changes, right? That means A not necessarily equals to BB, not necessarily equals to AB. Okay? Then it becomes more complicated. So, okay, this is the definition of non-ideal. Then the question is, I have a piece of alloy. Okay, one is the copper zinc alloy, the other is the nickel copper alloy. For you, it's just piece of metal. The other one is also piece of metal. How could I know which one is more ideal, which one is more non-ideal? How could I tell? Right? That's the question. Right? How can we distinguish them experimentally? Right? Okay, so right now let's assume this kind of experiment. Okay. Okay, so right now let's think about the ideal. Let's talk about the ideal solution. Okay, for example, like the ion nickel solution, it's very, very ideal, but it's not pure ideal. Okay, it's more ideal than something else. Okay, so for this end is ion, for this one is nickel. Okay, and this axis basically is the X nickel. Okay. Again, nickel ion solution is not ideal, okay? But it's more ideal than others, okay? Because ion and nickel have the similar electron structure and ion radius, okay? All right, so for example, I'm drawing that one. Could you please erase what I'm writing here? This is a tank, okay? This is not diagram, it's a tank. Sorry about it. This is alloy. Okay. This one, okay? Right now, this is a piece of metal, right? And on top is just a vacuum. It's just a vacuum, okay? And then I heat up this alloy to the very high temperature, okay? And then we start to generate metal vapor in the chamber. Okay, we start to generate nickel plus ion vapor. or gas. Okay? Can you understand what I'm saying? You can observe this phenomenon. Why you're laughing? You're smiling. What's good?
No.
Okay. Anyway.
I'm thinking, Professor, what will happen to me? Inhale this air.
It's closed.
You got anything?
Anyways, so have you ever noticed? You don't use this kind of the light bulb anymore. You know the tungsten filament light bulb. Have you seen that before when you were kids? You notice that after a period of time, the surface become dark. Okay, this is because tungsten got evaporated. Okay, you cannot see the vapor. It's not like the moisture of like the. You can smell it, you cannot. Okay, it's a tungsten, but you still can see it's vaporized. Okay, and it's the leaf escape from filament and deposit in the glass. Actually, we can make use of this kind of phenomenon to make some very long lifetime light bulb. I can explain later. But anyway, so this is okay. Consider inside it we have X nickel, we have X. That is the fraction of nickel atoms and fraction of iron atoms in the solution. Okay, and then when we evaporate them, the molecules, the atoms have the trend to escape from the surface into the vapor, right? For the nickel, for the iron. Okay, go to the vapor. Okay, and then we have another tank. This is the ion, pure ion, and we also have the pure nickel. Okay, and then we still do the same thing. We warm it up. Go to this gas. Okay. Correct, everybody? Then think about one thing. So because of interaction between ion interaction and ion nickel interaction roughly the same, do you think the mixing will change the evaporation rate of the ion?
No.
Will not, right? Will not. Understand something? Will not, because the only thing that drag or keep ion inside the liquid or inside the solution is the attractive force, right? But since nickel gives the same attractive force, the similar level to the ion itself, right? So the evaporation rate is the same, right? Compare with the pure ion or compare with the pure nickel, correct? So they have the same evaporation rate. Then what's the ratio of nickel and ion inside the vapor? Inside a void is X nickel, 2X ion. What about in the vapor? The same, right? Okay. This is the ideal solution. Okay? Right now, let's consider another scenario. We have copper plus ion. Okay? Copper plus ion. The reality is the copper and ion doesn't like each other. They do not want to stay with each other. Okay? They repel each other. Okay? Just like, okay, so then I start to warm it up. And in this case, actually we can see that the ion is very small. This one is very close to 0%. It's very close to 0%. Okay? That means we only have a trace amount of the iron inside. Okay? Then I start to warm it up. Okay? Because the copper doesn't like ion. When we warm up, what will happen?
It will evaporate.
The iron will go evaporate faster,
Yeah.
right? That's the ideal case, right? Then you will find that actually inside the vapor, the X ion in vapor is larger than the X ion in the solution. Okay? You know what I'm saying?
Can you explain it once again?
Because copper doesn't like ion. Think about it. You are going to the conference. You are going to the social club. Okay? And everybody like each other. And you are the last one coming in the club. You also like everybody. You just stay there. And then you don't like anybody inside it. You just escape, right? The same thing here. The copper doesn't like iron, iron doesn't like copper because the molecular structure is so different. So when you warm it up, the iron will escape faster, right? Will escape faster than the pure iron case.
Iron will escape faster or copper will escape faster?
Because, that's a good question. The copper, think about it, you are the only one doesn't like everybody. So you escape first.
Okay.
But the copper just stay there as your own, okay? But if we have another tank, okay, it's still copper and ion mixture, okay? And then for that time, the ion percentage is approaching 100%. Then the copper goes faster. You know what I'm saying? The
The
copper goes
concentration
faster.
of each element depends like
Is that-
which
is that-
one is going to escape fast.
Depends on which one dominates, okay?
So the dominating one will stay, right?
Dominant will stay.
Stay.
Yeah. So, and in the textbook, you can find that. Let me start talk this one, okay? So, we define a kind of the parameter. Let me see. Okay. We define a parameter, we call it the activity, okay? We define a parameter called activity. Okay? We can define a parameter of activity. The activity I experimentally can be measured in that way. So it's the partial pressure of I divided by the total pressure in the vapor. In the vapor, okay? This one is, we call it the activity of the element, of the component, okay? And for the ideal solution, you can see that, for example, this is xi, this is ai, okay? So because it's the ideal solution, the ratio doesn't change, right? And then the partial pressure also equal to this kind of molar ratio here, right? Then the activity and the fraction inside the solution just have the linear relationship. They just equal to each other, correct? This is the ideal gas, okay? This is the ideal solution. And this kind of the behavior, we give it a special name, I forgot this name. Oh. This kind of behavior, we call it Raoult law. How to pronounce that one? R-A-O-U-L-T. Raoult law, okay? And for this one, okay, for that one. For this one, okay? We just draw one by one. So for this one, is the copper dominant, okay? Then the X ion tend to 0, and this one is X ion tend to 100, okay? Then you will find something like this. So this one is Xi, this one is Ai, okay? And when the ratio is slow, when the ratio is low, okay? Again, this dashed line is the ideal case, okay? It's the ideal case. Basically follow that from the Raoult law. And at a low concentration, in the low concentration, we can call this one is Fe, okay? This one is Ae, just make the specific, okay? When the concentration of the Fe is very small, you can see that it's evaporated faster, right? Then the activity actually is higher than the ratio, than the molar fraction, correct? So you can see when the ratio of when the fraction of the ion is small, it's evaporates faster. Then the activity is larger, right? It's going that way. But when the ions start to dominate, it just evaporates as if there's no ion inside. It's just ignore the effect from the copper, right? So then, when the concentration is very high, it tends to go back to the ideal case. All right? And for the copper, the same thing. X copper and activity copper. Okay? When the concentration of copper is low, it goes up, and then it goes back to the original track. Okay? 9 points?
So how do you know which one is dominant?
Oh, you should know. We don't mix them. This is fabricated by you. I add in the lab. Okay, just add 1,000, I mean 1 out of 1,000 ion inside the copper. You know the copper is dominant.
So
Okay.
here this XFE is the Fe dominated one, and XCU is the copper dominated one.
Copper dominated when XCU equals 1. This is the
Yeah, so that is
this end is
Okay.
copper dominated.
Okay.
This end is ion dominated. Of course, you can put these two charts together. You can put the two charts together like this, okay? So this one is X ion. So on this end is ion dominate. On this end is the copper dominate, right? On this end is copper dominate, right? And then you can see on this axis we can put AFE, and on this end we can put A copper, okay? For the ideal case, okay, this one, the AFE should follow this curve, okay? And the AGU should follow this curve. But the reality is something like this. Okay? Something like this. You know what I'm saying? That means there's a funny thing, okay? There's one thing very careful. We know that this is X copper, this is X iron, right? If we put them together, they equals 1, correct? But if we consider the solid curve, when we add A iron and A copper, they are not equals to 1 anymore. Okay, they are not equals to 1. Okay? You understand something? Because X ion plus X copper always equals 1. But it's not necessary for us to have this conclusion. Okay? It's not necessary. Okay? We may have more copper inside vapor than the ideal case. And the same thing, we may have more ion in the vapor than the ideal case. Okay? We don't have this kind of relationship.
So the dot one is denotes the ideal case.
Yeah, the dot one is the ideal case. And solid curve is the real case.
So always this point, this intersection point, it's for real case is higher than the ideal one.
No.
That means.
No. This only work for the two molecules doesn't like each other.
Okay.
If they like each other, we will find lower value. Okay, it's going down. Okay. If you have a repulsive interaction between molecules, between different molecules, we have this kind of curve. If you have attractive interaction, having something like this, it's going down. Okay, that means activity is lower than expected, right? Because you have more attractive force to keep inside the liquid, inside the solution, than vaporize it.
So we always have a guess. If it is repulsive, then it's going to be like that.
Yeah.
And if it's attractive, it's going to be.
Yeah. So that means by measure the partial pressure of the gas, we can tell whether it's ideal or not. And we can also tell whether there are two types of atoms are repelling each other or attracting each other. Okay? You go to the bar, you go to the club, and you find, oh, everybody always doesn't look like me, but they really like me. You just stay there. Yeah. But I think everyone be kicked out from the gym or something. Don't like me.
With the unit of the molar fraction, there is no unit. So it
1%, 2%.
sums up and becomes 1. What is the unit for the activity?
It's still no unit because it's just a partial pressure divided by the pressure.
So there is any reasoning to summation to be 1?
No. A not necessary to be 1, but the fraction of the should be 1, right?
Okay.
You have 5% of iron, definitely have 95% of the copper, right? Okay. Right now, you know how can we tell the difference between.
So essentially, the only all the way on the left, that graph is only expressing on one hand side a copper dominating solution and iron dominating solution
Yeah.
together. That's it.
Yeah, exactly. This part is pure ion. This part is pure Pure ion, pure copper, pure ion. And then in between is something mixing. Okay? And this one is activity. Basically, it's the partial pressure of the copper compared with the vapor pressure of the pure copper. Okay? This is the partial pressure of the ion in the mixture divided by the pressure of the pure ion gas. Okay? That's the reason. At this point, they are not necessarily equal to 1.
So the left side will be XFE and this right side will be XCU, right?
No. Oh. I think this is wrong. Sorry about it. This one should be XCU. XCU equals 1. You have XCU equals 0. You have pure ion.
Yeah, so
XCU
that's what
equals
I'm
1.
saying. We can represent it as like XCU this side, FE this side, XFE this side, right? 100% FE.
Yeah. Okay. After knowing the experimental solution, we're going to do some calculation. Okay? Then the question is, we know that the driving force or driving factor for us to form the solution of form this ideal solution is the change of the Gibbs free energy. Correct, everybody? And although the interaction in this one doesn't changes, but we still can form a solution. That means the Gibbs free energy also got lowered down, right? For the non-ideal solution, right? Because as long as the solution forms, that means the is from the Gibbs free energy point of view is preferred, right? We also have the lower free energy. But the question is, for that one we know that it's very simple. The change of Gibbs free energy typically only equals to the GS, the TDS, right? But what about this one? We know that we not only have the TDS changes, right? We also have some change on the enthalpy as well. Correct? Because energy changes. The interaction energy changes. The entropy definitely change. How can we get this? How can we calculate this term? Okay, how can we calculate this term? Okay, that's a question. Okay.
Temperature.
No. Temperature is the same. Temperature is the same. The reason is the most important. I mean the difficulty is like this. Since the interaction between the molecules is always the same for the ideal solution, and the contribution to the enthalpy change is only the configuration entropy, right? But if the energy level also changes, the entropy will not only come from the configuration, may have some other factors. We may have some other factors. But think about it. Let's talk about this one. So, for example, we have the ion, we have the ion, we have ion, we have ion. We have ion. Okay? If the ion doesn't like copper, where the copper should stay? Probably stay here, right? It won't stay here, it won't stay here, it won't stay here, it won't stay, just stay here. Right? So that means the original calculation like this may not work. I mean, we can use this one to calculate the entropy change just because A and B are equivalent. Right? They can all, I mean, any A can occupy the place of B, and any B can occupy the place of A. But if these two atoms have different kind of the interaction strength, then the configuration can be different, right? For example, if you, I mean, we're going to talk about that matter. We talk about ion and copper, ion and carbon. You know that it can form some FCC structure, it can form some BCC structure, right? So it's not like the ion and the copper can randomly exchange. They have their specific configuration because of interaction there. So that means we cannot use this one to calculate the entropy anymore. We cannot calculate the entropy, then we have no way to calculate the, or to measure the change of entropy directly by using this equation. Then how can we do that? Okay, that's the question. Okay, to answer that question, we need, first of all, let's be really easy, okay? So how people solve this problem originally? We do not, I mean, if we do not know the change of the entropy, we do not know the chemical potential, correct? Chemical potential basically is the molar Gibbs free energy of each of the compounds, correct? If we cannot measure the change, we do not know, we have no way to calculate that one, we cannot calculate the chemical potential inside the solid and inside the solution anymore, right? And how can we do that job? Okay, we can do the job in that way. Practically, we can measure them. So how can we measure them? Still the same way. So we have alloy, A and B alloy. Okay, A and B alloy. But remember, this is the non-ideal solution, okay? We warm it up. We form the gas, okay? We form the vapor. Okay, we have A plus B. Correct, everybody? We have A plus B vapor. But right now, this one is under thermal equilibrium, right? This one is under thermal equilibrium, right? The system. We have vapor, and vapor A is in thermal equilibrium with A component inside the alloy. And vapor B is in thermal equilibrium with the B component in the alloy. Then what will happen? We'll have mu A in the vapor equals to mu A in the alloy, okay? And mu B in the vapor equals to the mu B. Okay, this is the fundamental of thermodynamics, right? We cannot know what's the mu A inside alloy, but we can measure the mu A in the vapor, right? We know the mu A in the vapor. Okay, and then we just need to know how the mu A change. I mean, by measuring how the mu A change in the vapor from the pure mu A vapor, we can calculate the entropy change, right? Think about it. So we also have a tank of A, pure A. We also have the tank of pure B. Okay? Then we have the mu A none here. We have the mu B none here. Okay? This is just the pure A vapor and the pure B vapor, right? And then inside it, we have the mu A none, also mu A none. That's mu none. Correct, everybody? So that means experimentally, we do not need to measure the chemical potential in the alloy. Instead, we can measure the chemical potential in the vapor. Okay, because they are equal to each other. We can directly just measure this term, measure this term, measure this term, and then calculate what's inside how the Gibbs free energy change in the solid or in the solution. Correct, everybody? Because under thermal equilibrium, the vapor and the alloy share the same chemical potential, right? Then the change of the chemical potential, I'm talking about molar chemical potential, okay? Simply equals to XA times mu A vapor minus mu A none plus XB mu A vapor mu B vapor and mu B none. Correct, everybody? Right? This is a change in the vapor phase. I'm not talking about the change in the solution, but that's same. Okay. How this one change? Remember, I mean the dg because we don't need to consider the entropy change anymore, right? We have to configure that change. For the ideal gas, okay? For the ideal gas, if the temperature doesn't change, for the ideal gas, okay, we know that dg equals what? Equals to VdP plus SdT, right? If these two if all the tanks in the same temperature, we don't have this term, then we don't need to consider entropy change, right? We don't need to consider this part, right? Still, we talk about the molar, okay, this molar. Then this one is what? This one is RT divided by P dP. Correct, everybody? And then we have the delta Gibbs free energy change equals to what? Is RT ln P. Correct? That's a change of Gibbs free energy. or the change of the chemical potential, right? This is the molar Gibbs free energy. And the molar Gibbs free energy for pure element is simply the chemical potential. Correct, everybody? Use that equation here. This one will equal to x1 RT ln. This one is a PA, okay, inside the vapor. And this one is the pure PA, okay? And plus XP RT ln PB in the vapor plus the pure PB vapor. Correct, everybody? Basically, you can measure experimentally. You can measure the partial pressure of A, get this term, and measure the pressure, the saturated pressure of A, give to this term. Okay? Oh, this one. This one is the partial pressure. This one is the saturated pressure. Correct, everybody? Right? Okay, let's talk about the ideal case. For the ideal case, we know that the partial pressure of A, for the ideal case, okay? For ideal case, the partial pressure of A simply equals to XA divided by the saturated pressure, correct? So this is the Dalton partial pressure law. And for that one, it simply equals to PBV simply equals to XB PB, right? Correct? And then we can put together, if you want some, the change of different, just go back to the ideal case. Correct, everybody? If this is the ideal solution, by using the Dalton partial pressure law, this equation just change back to the ideal case, right? But since it's not ideal, it's non-ideal. This term is not equal to XA anymore, and this term not equal to XB anymore, okay? Instead, they equals to ln activation of A plus XB RT ln activation of B, okay? Let me redraw that chart so you have a better idea.
For that, VDP you just erased, is there a subscript on it?
Huh? Oh, I erased something?
Was it V sub M?
Which one?
You just erased it.
Oh, sorry about it. Do that. Oh, it's M, I'm sorry. Yeah, it's M. And my handwriting bad, sorry about it. Let me draw that, okay? But for that one, but for this equation, you simply do not need worry too much about this one, whether this one is for ideal case or non-ideal case. You can use this equation for both ideal and non-ideal case, okay? Let me explain to you. So this one is AA, this one is AD, okay? This one is XB, okay? And on this end is pure A, on this end is pure B, okay? For the ideal case, we already mentioned. So the activation of B simply is the ratio of B. And the activation of A is simply the ratio of A, okay? Then the equation simply become XAA RT ln XA, okay? But for the non-ideal case, for example like this, okay? This one is, this curve is AA, this curve is AB, okay? We simply use the solid curve for the non-ideal gas, okay? Got the points? So for non-ideal gas, we use these 2 points to calculate the change of the Gibbs free energy. But for the ideal case, just these 2 points. Make sense?
Can you repeat that real quick?
Okay. So from that equation, you can see basically the change of the Gibbs free energy is the ratio of A, RT ln activation of A. So we use this point. This is activation of A, right? But for the ideal case, for the ideal solution, we know that activation is simply a solid line. So that activation actually is here, right? So this is activation of non-ideal gas. This is activation of the ideal gas, okay? And the activation for the ideal gas simply equals to the ratio, okay? So you can see that equation will go back to the ideal case. And in the textbook, you can find that they do not explain how that equation comes out. They just told me, okay, for non-ideal case, that is equal to the x times RT log activation. They simply do not explain what the activation means. But I hope that from this class you will know. If you read the textbook, you will not get confused. Hopefully, you will not get confused. Okay? Any other questions for this part? Again, the activation definition is the partial pressure of the I component generated from the alloy compared with the saturated pressure generated by the pure element. Okay? Got my point? That's the activation. And if the solution is ideal, the partial pressure divided by the total pressure simply equals to the fraction, the molar fraction, right? But if we consider the repulsive interaction, if the two molecules are repelling each other, the partial pressure goes up, right? If they are attracting each other, the partial pressure going down. Okay, that's the reason for the repulsive interaction, the activation is higher than the molar ratio. And for the attractive interaction, the activation is lower than the molar ratio. Okay? Make sense? And from this one, we can do the calculation. From this one, we can do the calculation. Basically, you can do something like this. We know this one. How can we do the draw? In order to calculate the change. Okay. Anyway, can you erase this part? So right now we know how the Gibbs free energy changes. Then the question is how the entropy change. And we already mentioned that we cannot calculate the entropy in the original way, right? It's Na plus Nb factorial and divided by Na Nb. We cannot do that anymore. We can change another way, okay? By using a function or equation name of what? We can use the relationship, we call it the Gibbs Helmholtz. Oh, this guy shows up together. I think these two guys don't like each other, but it seems like they show up together. Anyway, the equation tells us partial delta G T partial T divided by T equals to minus delta H divided by T squared. Okay? You can go back home to find how can we get this solution. This is called Gibbs Helmholtz equation. Okay? Go back home to find how can we derive this one. Basically, it's simple. So we know that the Gibbs free energy equals to D minus Ts, right? So then G divided T equals to H divided by T minus S. And then you do the partial derivative and find out this conclusion. Okay, and if we know that partial S, partial T, this is probably some thermoconducting, I mean, or like, is something like this one is the capacity. So you can find it, you can figure it out. Okay? The textbook, there's some drive how we can get the equation, but if you cannot find it, just check online. It's two-step, I mean, deduction. It's not very complicated. We just know we have one equation here. Okay? By using that equation, we can just put the change of the Gibbs free energy into this equation, and we can calculate how the enthalpy change. Okay? If we know how the enthalpy change, if after we know how the entropy change, we will know how the enthalpy change. Right? Got my points? Basically, for the non-ideal gas, we calculate the change of free energy first, or we measure the change of free energy first, and then use the Gibbs-Helmholtz equation to calculate change of enthalpy, and then we can calculate the change of the entropy. Okay? Make sense? And the trick when you do the experiment, or when you understand the theory, the trick is we have no way to directly measure the chemical potential inside the alloy, but we can vaporize them and measure the chemical potential in the vapor. And the chemical potential in the vapor share the same chemical potential in the alloy because of the thermal equilibrium. Okay? And the thermal equilibrium pressure the same, temperature the same, chemical potential the same. Make sense? Okay. I think that's pretty much. I was talking about something about light bulb, right? You still have 2 minutes. I will now release you guys. Okay? Light bulb. Light bulb. Okay. Do you know that in your car, the headlight is also a constant light bulb, right? It's very bright, but the lifetime pretty long. And if you open up, you cannot see the constant got coated on the light bulb surface. Even it's broken, it's still crystal clean. What's the reason for that? Do you know what's the reason for that?
What's the question?
Are
Okay,
you talking about the light bulb itself or the cover, like the clear part?
I'm talking about the inside the light bulb.
The
Just the bulb
tungsten,
itself.
Just the bulb itself.
coil, right?
Huh?
You're talking about the tungsten coil, right?
Yeah.
Well, you're talking about like how it'll coat the glass?
I'm talking about, okay, think about it. Originally you have a light bulb looks like this, right? Right? And after a period of time, you'll find that the surface of bulb become dark, right? And probably you can find some old bulb. If not, you cannot find that anymore, but probably look around, probably in your parking garage, find some very old light bulb. If possible, you can find our surface coated by tungsten. It's coated by tungsten, okay? Because it's evaporating, But for your car, the light bulb looks like this, right? Something like this, and you have something, you have some pin. And inside it, you have tungsten wire looks like this. Right? It's very tiny, but still tungsten, still the cover of glass. You can take it out, even if it's broken. You cannot find any kind of tungsten deposition on the surface. Until the end of life, the surface is still crystal clean. Why the tungsten doesn't coat it in the inner surface of the glass? And why this light bulb is very hot. I mean, the working temperature of this light bulb is approaching the melting point of tungsten. But why the tungsten still survive for a very long period of time. But for this time, traditional light bulb doesn't work.
Because it fills with air. Halogen.
It's not, huh?
That's a halogen.
It's halogen. It's halogen. But do you know how the halogen works? Why is it called halogen bulb? Do you know why it works?
Tell us.
Okay. So this one typically filled with iron dye, or this one, how do you say that? Bromine. So the reaction, they have some chemical reaction inside. Okay? So we have the low temperature, the tungsten have really high temperature, and the surface roughly have the low temperature, right? And then when the pressure is high, the low, and the temperature is high, we start to trigger the reaction between tungsten and iodine. Okay? So this compound forms, compound decomposes when the temperature is high and forms when the temperature is low. Okay? That means the iodine, tungsten, this kind of compound is stable at a lower temperature, but it's unstable at a high temperature. Okay? And it's a gas phase. Okay, that means whenever you have tungsten deposit on surface, we start to have the reaction. Okay, the tungsten will form compound with iodine. Okay, become vaporized, and then because the tungsten has really high temperature, it decomposes here, and tungsten redeposits back to the filament, and release the iodine, and the iodine will interact with the tungsten deposit on surface and put it back. You have the circulation inside. That means tungsten keep evaporating, but the iron dye keep it bringing back. That's the reason it has a really long lifetime. And the very interesting phenomenon is that, go back home, take the car from the desk, take the ball from desk car, okay, without telling him, you'll find something very interesting. At the very beginning, a brand new tungsten filament is pretty round, okay, surface is very smooth. But at the same time, you start to build the tungsten crystal on it. Okay, it's become very rough, but become very shiny. That's because you have this process, we start to develop the tungsten crystal on it. Okay, originally it's multi-crystal, but right now start to grow the single crystal on it because of reaction. Okay, basically this is one way we synthesize the large bulk of crystal by using this method. Okay, for example, some material you cannot simply melt them. We cannot melt. Sometimes they just decompose it, or the melting point pretty high. So we use this method to grow crystals. Okay.
Vapor
So,
deposition, you mean?
huh?
Chemical vapor deposition, you mean? Kind of.
It's not vapor deposition. This method we call it chemical vapor transport. Okay. Anyway, so this
To
is
grow single crystal of that.
huh?
To grow a single crystal.
Yeah. Open the box, we can see that we have tungsten crystal. Anyway, so okay.
Professor,
Professor,
we put iodine or bromine inside. Can
Huh?
we just make it?
What's that?
No,
Yeah.
we put only iodine or only bromine, right?
No, you can mix them. You can mix them.
Why-
Sometimes people, huh?
Why can't we just make it from say airless or nothing inside?
If you put nothing inside, the tungsten just deposit on surface without coming back. You know what I'm saying?
We don't have to get a six-figure biological shop.
Ready?